Hello guys, this is Paul McWhorter from TopTechBoy.com, and we're here today with lesson number 21 in our fabulous series of Arduino tutorials where you are building a 9-axis inertial measurement system. I will need you to pour yourself an extra large mug of iced coffee because you are going to need it today because we are going to work with quaternions. Let me give you a warning. Many who have dabbled with quaternions have gone mad because it's almost like you could just almost understand them, but understanding the quaternion just escapes you. Okay, so I will warn you that you might go mad. It's sort of like a moth to a flame. Don't look at them. Don't look at them. Just you want to get in and out as quick as you can. Quaternions will drive you mad. But we're going to play around with them a little bit today, and it's actually going to solve all of our problems. And you're going to see all of the things that don't work real well about our project. All of those little problems are going to go away when we start using quaternions. And so this will be somewhat of a tough lesson, but I am confident that you are going to be able to be successful. So let's kind of review where we left off in lesson number 20. We were taking raw data from the accelerometer, the magnetometer, and the gyros, and then we were coming up with estimations for roll, pitch, and yaw. And then we were sending those over to Vpython, and then keeping track of our vectors. We were able to, for relatively small tilts, let's say less than 45 degrees, we can track the yaw, we can track the roll, and we can track the pitch, and we can do roll and pitch, we can do all these different things. But because of all the approximations that we made in the math, if we do something like, let's say that we start really pitching nose down, okay, you see how it flipped? Do you see how it flipped wrong way? The green flipped around. Okay, you see how it flips? And so if you start tilting more than 45 degrees, you start getting some glitchy behavior. Even at 45 degrees, when you're doing roll and pitch, it doesn't work real well. So we did a whole bunch of math. We did a whole bunch of approximations. But then when we get to the end of the day, those approximations turn around and sort of are going to bite us. And so to get around it, what you have to see is that just doing your project on Euler angles, it just really, you kind of hit a wall that you can't go any further. And even like I would have you sort of think about it this way, that Euler angles are three numbers, roll, pitch, and yaw. And then if you think about it, we can think about where the position in three-dimensional space of this tip of this vector is with three numbers, like the x position, the y position, and the z position. Now I can position this in, in real three-dimensional space. But the problem is, if I start rotating, you can see that it's almost like you really need a fourth number, kind of like x, y, and z, and then rotation, a rotation angle around x, y, and z. And so we sort of wave our hands and kind of make do with the three numbers of the Euler angles. But what also happens is there's ambiguity in the Euler angles. And so let's say that I showed you, this little thing here. Okay, and let's say we were pointing this way. Okay, we were pointing this way. All right, and then I covered it up and I came back later and we were pointing this way. Well, with Euler angles, what you would say is, you yawed 90 degrees, okay? But in fact, I didn't yaw 90 degrees. I rolled 90 degrees, and then I pitched 90 degrees, and then I rolled minus 90 degrees. So you see, there are many different roll, pitches, and yaws that would get you to the same endpoint, and because of that, there's a built-in mathematical ambiguity associated with Euler angles. Also, like if you think about this as an airplane, if you think about it like the direction that I'm going north, I'm going east, I'm going northeast, that all makes sense, right? But if I roll 90 degrees, Now this thing no longer has any sense as far as makes any sense as far as north and south, because all of a sudden I'm orthogonal to the plane of the earth, so north and south don't mean anything anymore. But yet I am absolutely oriented in 3-dimension, right? You see, I am oriented in 3-dimension, and so I need to be able to mathematically describe that without getting all confused. And so Euler angles, they're good for little simple things, but once you get to just wanting complete free body rotation in 3 dimensions, Euler angles are not going to get you there. So let's start talking about quaternions. And the way I'm going to introduce quaternions again, if I were one, I tell you, you don't need anything in your coffee. If there was ever a lesson that you might want a little hard stuff in your coffee, this would be the one. But I won't condone that. I will not condone that. We're going to get through these quaternions, right? So the best way I can describe quaternions is to maybe take you back to something that you know, and then we will start developing it from there. So what did we learn the first day of first grade? We learned about the number line. Okay, we learned about the number line. All right. And all the numbers on the number line, right? There's the integers and the real numbers and the rational and the irrational and the whole and the natural, all these different things. So we spent all this time living our life comfortably on the number line. But then one day, probably about 9th grade, they came along and they told us, oh, by the way, there's all these numbers that we never told you about. They are the imaginary numbers. And what you have is you have another number line that we never told you about, and those are the imaginary numbers. And so like if this is 1, 2, 3, 4, our friend the number line, okay, 1, 2, 3, 4, there's also this number I. I is not a variable. I is not a letter. It's a number. It's the imaginary number. And this is I2. And this is I3. And you can have negative ones, minus I, minus 2I. And then here you get minus 1, minus 2, minus 3. And then how is it that, we're living our life on the number line? How do you fall off the number line? If you take the square root of a negative number, it kicks you off of the number line, okay? And if you get kicked off the number line, you don't want to just float around in space just like lost in space. You got to have something to grab onto. Well, what do you grab onto? You grab onto this so-called imaginary number line, all right? And what are some things that we know about the imaginary number? Well, the square root of negative 1 is equal to I, and therefore we can kind of say that I is equal to I. We can say that I squared is equal to negative 1. I squared is negative 1. I cubed is equal to negative I, and then I to the fourth is, I messed up somewhere. Let's see. I is equal to I. I squared is equal to negative 1. I cubed is equal to negative I. And I to the fourth would be equal to positive 1. Okay, because it would be negative I times I, which would be negative I squared, which is negative 1, which would be negative 1. And so we have the nice result. So I is equal to I squared negative 1, I cubed negative I, and I to the fourth is equal to 1. And so these are kind of the rules of the imaginary numbers. And it's kind of unfortunate that they called them imaginary numbers because they're really very real, and most engineering problems you can't solve without using these imaginary numbers. But here's kind of a neat thing maybe you haven't thought of about imaginary numbers. Like let's say that I have the number 1. Okay, I have the number 1. And let's say I multiply by I. If I take 1, so I'm right here, okay, I'm right here, so let's draw a vector here, because we're all about vectors these days. I have a vector, the vector 1, in the real direction, and I multiply it by I. What does it do? I get 1 times I is equal to I, and where is I? I is up here, okay? So do you see that multiplying by I to the first power is the same as rotating the vector 90 degrees? So times I has the effect of a 90-degree rotation. Well, what if I multiplied by I raised to the 1/2? Okay, instead of multiplying by I, I'm going to multiply by the square root of I. All right, well, normally I don't like calculators, but this is a good thing, and you know, I'll put a link down below. It's kind of nice to have a graphing calculator. The TI-84 is a really nice one. So let's see if we can turn this thing on. And one of the things I want to show you, if you go to mode, and if you come down here, you can see that most calculators just operate as with real numbers. You can actually make this calculator work with imaginary numbers, and they work just, it does simple calculations for you with imaginary numbers, but you have to come in and you have to set it to a plus bi. That's sort of like the numbers have a real part and an imaginary part. So you got to set that up like that so that you can do imaginary numbers. And then if you look down here, you have under the period, you have the I button. Okay, so if you do the second and then the period, you will get an I. So let's just try that. Let's go second, and then I, and then what do I get? I get the number I. I'm going to try to clean this screen. This screen is like really, really terribly smudgy. Okay, so you see this calculator will work with I. So let's say that I'm going to take the number I, so shift period, I've got the number I, and now using this little caret, I'm going to raise it to a power. What power do I want to raise it to? Well, the 1 divided by 2. So I divided by, I raised to the power of 1/2. So I'm going to take my vector 1, and I'm going to multiply it by I raised to the 1/2. What do I get? Well, I get 0.71 plus 0.71i. So now I've got a real part and an imaginary part. Okay, I've got a real part and an imaginary part. So what that's saying is that I come out 0.7 in the real direction, I go up 0.7 in the imaginary direction, and I get a vector at what? Well, you guys that know a little trig know that that's at 45 degrees because I come out and over the same amount. So multiplying a number by I rotates by 90 degrees. Multiplying a number by I to the 1/2 rotates by 45 degrees. A 45-degree rotation. And so what you can see is that you can do rotations that what you do is you multiply by I, okay, and then it is your angle divided by 90. So I to the angle divided by 90 will rotate a vector by that many degrees. Okay, so you take your vector, you multiply it by I to the angle you want over 90, and then you will get that rotation. So let's see if we do 90 divided by 90, we have I to the 1. We end up on the I-axis. If we do the 45 degrees, that's I to the 1/2, and we saw how that works. So do you see that the interesting thing about imaginary numbers is multiplying by an imaginary number has the same effect as rotating a vector. And it's a lot easier than trying to keep track of matrices and cross products and all of these different crazy things that you multiply by an imaginary number and it's the same as a rotation. It's a really neat way to do it. Well, that would be neat and that would be good if all we were trying to do was yaw. Okay, if all we were doing was yaw, what is that crazy nonsense? Sorry. I just had a window pop up out of nowhere. Okay, so if all you were doing was yawing, I could do my bookkeeping by multiplying by an imaginary number and just keeping track of the complex math, and it would be a most elegant way of doing it. But the problem is I am not just yawing, I am also rolling, and I am also pitching. And I can't keep track of all of that with just one imaginary number. So what do I really need? You see it coming. You see it coming. I need 3 imaginary numbers. Okay. Now I need a room, right? So instead of having an imaginary number line, I'm going to have an imaginary room. And this axis is going to be my I-axis. This axis is going to be my J-axis. And this axis is going to be my K-axis. So now, instead of having an imaginary number line, I have an imaginary room. All right. Now, this is kind of like getting you towards quaternions. These are 3 of the quaternions. You sort of have like an X quaternion, which is in the I direction, a J quaternion, which is kind of in the Y direction, and then you have a Z quaternion that is kind of like in the K direction. All right. And so let me see if I can give you now some of the interesting things about quaternions. All right. These are some of the interesting things. Well, you already know this is our old friend I. So you already know that I squared is equal to what? I squared is equal to -1. Well, guess what? J squared is also equal to -1. And guess what? K squared is also equal to -1. So when each one of these is kind of working by itself, it's kind of like, okay, that makes sense. But then here's the problem. Now that I have more than one, I got to kind of figure out how they work with each other, how they play together. All right. And these are the rules as far as how they work together. If I have I and I multiply it by J, I times J is equal to K. All right. So if I'm here at I and I multiply by J, I don't rotate up to the J-axis. I rotate over to the K-axis. I told you, I warned you, this will drive you crazy. Okay, well, how about J times K? Well, that's equal to I. Okay, so if I'm at J and I multiply by K, that rotates me over to I. Okay, how about K times I? That is equal to, you guessed it, J. Right, K times A is equal to K times I is equal to J. And I'm just going to glance over here at my notes to make sure that I am not lying on these things. It's kind of hard to do quaternion math live on the internet. Okay. I need to find some definitions here to make sure that I am not lying. I am pretty sure that I am right. Okay. IJ is K, JK is I, and KI is J. Yeah, you can kind of see a little bit of a pattern developing here. All right, but now this is the one that will blow your mind. I times J times K is equal to what? Well, I times J is K, and then what's K times K? It's -1. So I times J times K is equal to -1. I'm sorry, but that's just the way it works. All right. So the other thing that's kind of crazy is J times I is equal to -K. All right. And so this is not commutative. Like normally in the real world when we're doing math, 3 times 2 is the same as 2 times 3. Or A times B is the same as B times A. The order doesn't matter. In this imaginary room in the quaternion world, the order does matter. And similarly, k times j is equal to negative I, and I times k is equal to negative j. All right. But with this craziness, hopefully what you can see is you are still rotating. I can take this vector and multiply it by one of these other quaternions, and it turns out to be a rotation. But it's just the rotation is a little bit counterintuitive, but this table kind of shows you what the rotations are. Now this is the crazy thing. Remember how I was saying that really to solve this problem you need 4 numbers? Well, we just have 3 here, so we've kind of moved from the real world over to the imaginary world, but we're still in this problem that to unambiguously really describe what's going on here in a complete free body rotation, we really need 4 numbers. And so what you end up finding is if you make your way into this imaginary world, what you find is you find a real number inside there, W. Okay, and so what you end up with is you end up with 4 quaternions. The first one is W, which is a real number, and then you kind of end up with X, Y, and Z, which are the imaginary numbers. Let's see, you can't see that. I am sorry. So the first quaternion is W, which is a real number, and then you end up with 3 imaginary numbers, X, Y, and Z, which kind of are in the I direction, the J direction, and the K direction. So if we can get these quaternions, as hard as they are to understand, all of a sudden all of our rotation just becomes really, really simple because it's a series of multiplications and everything just works very, very similar, very, very simply. Okay, so let's go back over here and let's kind of remember that what we are trying to do is we're trying to do a better simulation where things don't go wonky as I am rotating. Wow, you have got just a crazy bad view there, don't you? What were you seeing, my car keys? I've got quite a few keys there, don't I? Okay, so what we want is we want something that doesn't go wonky as you start doing these rotations above 45 degrees. So what we want is quaternions. So what I'm going to need you to do is open up an Arduino IDE. I have several here. Let me see if I can find a good one. Let's see. This looks like an empty one. All right. So we are going to get our, I hate Windows when it does that. Okay, we are going to get an Arduino IDE up. And what we want to do is we want to start where we left off. We want to start where we left off in lesson number 20. And so let's go back to the most excellent www.toptechboy.com and let's get lesson number 20, and let's get our Arduino code from lesson number 20. So if you just go there, and where did I put that silly little keyboard? There it is. Okay. I am going to control copy that code from there. And you guys, I'm not going to explain this code because I've explained it over the last 20 lessons, right? So you kind of, if you've been following along, you know it. But now I'm going to paste it in here. So now let's see what we were doing on the Arduino side. On the Arduino side, we were coming in and off of the B&O 055, the B&O 055 9-axis sensor, we were pulling the acceleration vector, we were pulling the gyroscope vector, and we were pulling the magnetometer vector, and then we were doing a lot of shucking and jiving to try to turn that into roll, roll, pitch, and yaw. Okay, we were trying to turn that into roll, pitch, and yaw. And when we were doing that, we were doing great damage to trigonometry because we were coming up with approximations, and we were doing the best we could with this kind of trying to solve a 4-number problem with 3 numbers is maybe the way I would put it. So we were pulling those, and then we were calculating roll, pitch, and yaw, and then we were sending roll, pitch, and yaw, and then we were still sending the system calibration numbers, and then we would go catch them over in Python and then start visualizing them. This is a neat little thing about this little sensor, and this is something that we hadn't talked about before because I didn't want you to run from the room crying like a little child. But there is a way that you can just go and directly grab the 4 quaternions from the BNO 055. And that's one of the reasons that this sensor costs $35 instead of costing $6 is it has an onboard algorithm for in real time to continuously generate those quaternions so that you can more elegantly solve the problem. So what I'm going to need is I'm going to need to look at my code over here, and we were over here. All right, so what we are going to do is we are going to we're going to get rid of, we're not going to get these two, we're just going to do one pull. Okay, so on this one, IMU vector, okay, and there are going to be 4 numbers, so we're going to put a 4 here, and now we are going to pull this vector into the name quat, okay, and then we are going to do an IMU.getVector Adafruit BNO 055, and I sure hope I can spell quaternions when it matters. Quaternion. Okay. Okay, I think that should work. Let's run this just to see. Let's run this just to see. I guess, no, I got to get rid of some of this other nonsense. Okay, so now this command line, and guys, I'll put this on the lesson 22, toptechboy.com, so you can see this code. But do you see what I just did here? Instead of pulling accelerometer or gyro or those other things, what I am pulling here, I am pulling the quaternions. All right, so now this was just trying to calculate estimations of roll, pitch, and yaw. And then I come all the way down here to where I am calculating size. So all of those crazy things I am not going to do. Okay. What I am going to do is, at this point, I have grabbed the 4 quaternions. So what I'm going to do is I'm just going to send the 4 quaternions over. So it is going to be quat.x, okay, like that. Let's start with w. I'm going to send it as quat.w, okay. Then I'm going to send the quaternion.y, and then I'm going to send the quaternion.z. I forgot xw, x, y. And then we're going to have another one, because remember before we were sending 3 numbers, roll, pitch, and yaw. Now I'm sending 4. So I'm going to copy this, and then I'm going to put it here. And so now I'm going to send W, X, Y, and Z. So I am sending W, remember, is that real part. And then this is the quaternion in the I direction, the quaternion in the J direction, and the quaternion in the K direction. And then we're still going to send over our calibration numbers from the BNO 055, just because we might need them later. All right, this was kind of crazy, right? This was kind of crazy. Let's get rid of all this stuff up here that we don't need. I don't think we need any of this stuff anymore. We don't even need this millisecond stuff. So what all am I getting rid of? I'm still loading my libraries, but everything from the loading the math library down to this define thing where I'm define BNO 055, where I'm starting to turn the sensor on. we're going to get rid of all that. So we load our libraries, we turn the thing on, we do a little bookkeeping with the crystal. We don't need this milliseconds old equal milliseconds because we're not integrating that gyro anymore. We will get the calibration data here. That's good. We will pull the Quaternion vector, and then we will print the Quaternion vector. Why are we printing the Quaternion vector? It is going to send it over to Python. I will need you to hold your breath this time. Oh, download. Oh, it wants me to save it. All right. What is this? Save it. Okay. Oh. All right. They didn't set it up as a vector. What they did is you just say, okay, you do it this way. I'm sorry. IMU : All right. Do you see that? IMU : And what you say is get the Quaternion. Get the Quaternion. So IMU : Quaternion. Get rid of all the rest of this nonsense. IMU : Quaternion. What name do you want to put it in? Quat. Okay, we're going to call it Quat. You get to choose it, but whatever you use here, you need to use down here. And that is going to be equal to BNO. Did we call ours BNO? I think we called ours my IMU. So we will call it my IMU. You see, this is what you're talking to, the object that you're talking to. And we named the object my IMU up here. So we will say quat equal get my IMU, or quat is equal to my IMU dot get quat, like that. So we're talking to the IMU. We're telling it, hey, I want a Quaternion. I want you to put it in the name quat, and then go to my object, my IMU, and then dot what function, get the Quaternions, and then they should come into W, X, Y, and Z. And then up here we already got the system calibration. All right, sorry that I didn't have that right the first time, but we will continue. So let's see if that will download. Oh, up! I bet we didn't do a. We didn't put our semicolon there. Did you guys catch that? All right. Okay, and these were 2 extra lines of code from that other stuff, and so we want to get rid of those. That was from back when we were integrating the gyro to get our angles. All right, let's see how this looks. It's going to work this time. Oh, okay. I know why it doesn't work. We're probably running a, we're still running that Python program, and so that COM5 is still there. So please, please, please help me find. Okay. Let's kill that. All right. And now if I kill that, and now I will come back to my Arduino and we will run it. The tension builds. I think it's got, yeah, okay. Now, I'm just going to hit the serial monitor just to see if I have numbers coming over and they're changing right now. Okay, boom. You see I have quaternions, and as I move around, they're changing. Okay, you see they're kind of small numbers because if you take the, another thing I didn't tell you, but if you take the square root of the sum of the squares of the 4 quaternions, you should get 1. Okay, so you see they're all changing, but it's somewhat of a unit vector. I don't know if it's really right to call it a unit vector because it's operating in, you know, 3 imaginary dimensions and 1 real dimension. So I don't, that's kind of a crazy unit vector in a 4-dimensional space, which is more than I can really fully wrap my head around. But we're getting quaternions, and now we're ready to send them over to Python. Okay, so I'm going to kill this, and now We are measuring quaternions and we're sending them over. So now we need to go to Python and grab this stuff. The easiest thing to do is to come back to, let's see, where are we? We want to come back to toptechboy.com. Okay, and we want to go back to lesson number 20. Got confused there a second. All right, so we want to go back to lesson number 20, and we want to get all that code that we started with, this Python code down here. So I'm going to get all that Python code, and I'm going to grab it, and then I'm going to come over here and paste it. And then this was the visualization when we were sending roll, pitch, and yaw. But now we're sending quaternions, so if I'm sending quaternions, I had better catch quaternions. And I sent them in the order of W, X, Y, Z. I think I am going to confirm that. I came over here, I sent W, X, Y, Z. So I need to read them in that order. And so we come down here where, okay, we've got the while loop. And then remember, we read the data packet. We'll still do that. We split the data packet. We'll still do that. And then we calculated roll was equal to, we were reading roll. Well, that first number now in that split packet is no longer roll. It is what? It is the first quaternion, which let's just call it Q0. Let's just name them 0, 1, 2, 3, and that's W, X, Y, Z. Quaternion 0, quaternion 1, quaternion 3, quaternion 0, 1, 2, 3. Okay, so the first one is going to be Q0. I got to get rid of these crazy 2 rads, right? I got to get rid of all those crazy 2 rads. And so the first number that I sent was Q0. The second number I sent was Q1. The third number I sent was Q2. And now I've got another one. I've got to read that. I don't want to go in and start reading that other nonsense. So I'm going to get a control copy and control paste. And that one is going to be Q3. So right, I sent 4 numbers, 4 quaternions, and I am getting those 4 quaternions. Then I'm going to take out this print statement because I'm no longer getting roll, pitch, and yaw. Okay, so now I've got quaternions, and I've got to visualize them in Vpython. All right, I've got quaternions, and I've got to visualize them in Vpython. And that's the real question. How do you visualize them in Vpython that thinks in terms of like an axis direction and a rotation direction? Don't hate me, okay? Don't hate me. Get your coffee, okay? Get your coffee. Take a deep breath. What we need to do is we need to turn the quaternions into Euler angles. Why would you do that? Well, you see, this is the thing that's kind of hard to explain. You want to track position, and you want to do all of your bookkeeping, and you want to do all of your math and keeping track of who's where and what's going on. All of that you want to do with quaternions. And then, but the quaternions is this imaginary ether that you're in. At the last possible minute, you've got to come back to Euler angles and then display them. But you're not sitting and fooling around in the world of Euler angles. You're fooling around in the world of quaternions. And at the last possible minute, right before we do this vector display stuff, at the last possible minute, we snap back to the real world and we get our Euler angles back. Okay? So what I need to do is I need to convert quaternions to Euler angles. And who is your friend? Your friend is the Wikipedia. And actually, it's been a little disconcerting because let's see if this is, yeah. There's a lot of different websites that do the conversions differently because there's slightly different definitions on quaternions. But if we use these conversions from Wikipedia, they seem to play real well with the format of the quaternions that the BNO 055 is throwing at us. So what we can see is yaw is equal to the arctan2 of all these 4 quaternions. And then we can see the pitch is the arcsine of these quaternions. And then we can see the roll is the arctangent of all of these things. Now the question is, what is the chance that we can program these things in without making a horrible mistake? So we're going to do our best. Okay, we are going to do our best. So we've got our 4 quaternions. You also see why I named them Q0, 1, 2, 3 instead of W, X, Y, Z, because I knew that Wikipedia put them in this format, and you want to kind of use the same variables because this is going to be hard enough to put in there as it is. So I'm going to see if I can bring that window up again. I'd like to see both windows at the same time. So where am I on this? I'm on, just search on Wikipedia conversion between quaternions and Euler angles. And then you come down here and you get this, what's the difference between these two? Oh, this is just the more using the functions that would be in Python. There's subtleties associated with arctangent, so you really want to use in Python the arctan2. Okay. You can see those, and then I will come here and I will bring this up a little bit. Okay, so let's jump right in. So at this point we are ready to start coding up these equations from Wikipedia to convert our quaternions to Euler angles. The first one is roll. And we want to do this pretty carefully, so you guys watch me pretty closely. A tan 2, open parentheses, and then 2 times. And then it looks like we've got Q0 times Q1, Q0 times Q1 plus Q2 times Q3. I'm going to stop and check this because I don't want to have a bunch of errors. Okay, that looks pretty good. And then it is comma, so that was the numerator. Now the denominator of the arctan function is going to be 1 minus 2 times, and then it looks like it is going to be Q1 squared, the easiest way for me, Q1 times Q1. I don't remember the Python square function, so we'll just do it the kind of kludgy way, and then we have Q2 times Q2. All right, so that is the equation for roll. Let's take a look at it. Minus plus, plus. Okay, that looks pretty good. Then the roll, the pitch is pretty easy. The pitch is going to be equal to the arcsine of 2 times the arcsine of 2 times Q0 times Q2 minus Q3 times Q1. Okay, and I think I need another set of parentheses there for good measure to make sure that that 2 multiplies everything. Okay, so that looks pretty good. And now we are going to have yaw, and yaw is going to be equal to a tan 2, and then that is going to be 2 times open parentheses, and then we're going to have Q0 times Q3 plus Q1 times Q2. And then in the denominator, we're going to have 1 minus 2 times, and then open parentheses. Ooh, I see an error up here. This should have been times up here. Did I get all my other multiplication? Hopefully you guys were yelling at me, but 1 minus 2 times, and then Q2 times Q2, and then we are going to plus Q3 times Q3. And Python got unhappy there for a second, but it looks like it's going to survive. All right, so now I probably have an extra close there. So Q2, Q2, and then Q3, Q3. So when it glitched out there, it didn't get that. Okay, so that looks good. Yaw is arctan 2 times Q0, Q3, and then plus Q1, Q2. And I do, in fact, need to close that parenthesis. And then 1 minus 2, and then Q2 times Q2 plus Q3 times Q3. That looks pretty good. So now, I mean, we're almost ready. I think that we could just go ahead and run this. Now, one of the challenges is that we have sort of like an orientation system in Vpython, and then we've got an orientation system on the BNO 055, and we might have to tweak this a little bit to get the two worlds to align, to get the virtual world to align to the real world. But usually you can do that with just a little tweaking. But let's hold our breath. Is it going to run? Is it going to run? Signs of life. Okay, I need to get that in the field of view. Okay, so it seems like maybe it ran. Is there any signs of life? No signs of life at all. So let's see what happened there. Did we get an error? Let's see, line 23. A lot of errors. What is it not like? Let's see, roll, pitch, yaw. Okay, let's just try this again. I am not sure what happened there. I don't see anything obvious. It just seems like it was having trouble connecting to, okay. No errors yet, so let's see if we can move this thing. See, okay. Seems like we've got some signs of life, so the first thing we'll do is get those magnetometers calibrated. And then the second thing that we should do, as you know from earlier lessons, we should get the north aligned with the north. And so let's see here. All right, and let's make sure we have our magnetometers going good. And now what we are going to see is something crazy. Okay, we're not crashing, but this thing is not at all right. So let's see what happened. Let's see what happened. I will kill this. It was just not at all in sync. Ah, I see one error. Did you guys catch that? When I did the Q3, that should be the third number, right? There were 4 numbers. The third one, 0, 1, 2, 3. It's the 3 would be Q3. Okay, that would definitely cause part of the problem. So let's try this again. Wow, that was a scary one. Did you see how wonky that was when we did that? Okay, so now we're going to align north to north, more or less. Okay, now we're going to sling this thing around to get the magnetometers calibrated, and then we're going to come in, and let's see. It seems like that pitch is pitch, right? The pitch is pitch. Pitch down is right. Okay, but let's see. I think roll is backwards, right? Let's see his pitch. That pitch looks good. but the roll is backwards. The roll is backwards. Okay, so the easiest way to deal with that is to just change the sign of roll to a minus, and that should get that oriented correctly. It's like I said, I warned you, it's going to take a little tweaking to get these things oriented where they're like in sync with each other. But the good thing is it seemed like that it was rolling and pitching, looking pretty nice. Okay. And here we go. Let's see now. Okay, give it the old shaky shaky. Okay, and then bring the north to north. Okay, and so now pitch is pitch. The roll is roll. Okay, do you see the yaw is reverse? When I'm yawing, it's yawing backwards. Okay, the yaw is backwards as well. So I need to make yaw negative. Okay, and now we will come back over here. I should have killed that already. It doesn't like it if you don't kill it. Okay, now yaw is reversed, roll is reversed. This should be really close, I think, at this point. Okay, bring it back into your view. Get those magnetometers calibrated. It doesn't look like it came to life that time. What happened? Well, it says that it's happy. Okay, let's just try it again. Okay. Ooh, I put something very ugly there. I put the arctan. The negative is right there. I'm negating the whole thing. I hope you guys saw that. So that's why it didn't run that time. Okay. And it looks like my webcam has gone bad on me. Okay. Sling this around. Okay, and then let's point north north. All right, and then get the view where you can see it a little better. Okay, so now pitch is in the right direction, roll is in the right direction, and the yaw is yawing right. The only thing is that I am like, we are 90 degrees out of sync on yaw. And so when we just started this, the Adafruit documentation didn't give a lot of really good information as far as how this thing is oriented, what it considered to be the front. And all through this, we've been saying this is the front, so when this is pointing north, we should be at 0. But it looks like that the Adafruit library is using this as north. I think if we just subtract, pi over 2, that should fix that. So let's try that. Okay, let's try that. And I will come over here and we will come to yaw, and we are going to subtract np.pi, which is the easiest way for me to do pi, np.pi divided by 2. And let's see if this is going to work. Okay, so now we should be able to run it and come back over here. Okay, now there it pops up. Let's get it in view. Let's put north north, back up a little bit, get this thing calibrated, and now we're going to come in and look at that. The good news is it's oriented, the virtual world is oriented with the real world. Now let's try pitch. Nose up is working. Okay, that looks good. Nose down is working. Yaw 90 degrees. Yaw minus 90 degrees. Okay, now the big question is going to be roll. Roll is right. Boom. All right, man. Now what I want you to see is I want you to see how nicely this one behaves compared to, do you see how nice and perfectly smooth this is compared to when we were doing all the stuff with Euler angles and trying to do the approximations? Okay, let's see if we can roll all the way. Okay, then we can turn as we're rolling. We can pitch. Let's go all the way upside down. That looks good. Let's do a nosedive. Let's do a nose up. Let's spin it around while it's nose up. All right, man, this is just really incredible. Now what I want you to notice is just how smoothly that simulation is working now that we're using the Quaternions. Can you tell the difference? And also the really hard things, like if we roll to 90 degrees and then I can spin it while it's on that orthogonal axis, and that is pretty incredible. Okay, so a couple of things that I want you to think about is that if you're now going to work with this sensor in the real world, you're going to have to get the sensor oriented with the real world axes. And so it might be a little different. You might not want to subtract the NP pi over 2. You might want to just orient the sensor correctly with the real world, which I think is 90 degrees different than what we're doing here, or define north differently. And then you might have to tweak those signs on the roll and pitch as well. But usually with just a little bit of tweaking, you can get it working. But anytime you're going from the real world to the virtual world, or you're putting this device, you're putting the sensor in the real world, you've got to get your axes aligned, and sometimes it requires a little bit of tweaking like we have seen here. Okay, a couple of more things let me try and show you that I think are really neat. All right, I can't help myself. I really cannot help myself. I get things working and then I've got to just do one more thing. And what I want to do is I want to give you a bigger view so that we can see the simulation compared to the real world with a little bit better view. And so you don't need to do this. You can just enjoy your coffee here. But I am going to put a quick command in here, and I am going to Control F2, kill it. I am going to run it, and then I'm going to come over here to this view. Okay, this is kind of a little bit what I wanted, I think. Let me see, how do I fix this? Okay, yeah, this is sort of what I want here. I just am getting Wouldn't it have been nice if I'd done this before? I need a bigger window is what I need here. Guys, just don't hate me, right? Give me a chance. We've worked hard on this. This is 21 lessons, so this is... I'm making my window bigger. Control F2. You guys don't have to worry about this. I'm just trying to create a visually stunning view here. Okay, and now where did my thing go? There it is. I think I can actually make this work. Okay, so we calibrated. Guys, because there's things that I want to show you. In order to show you these things, I need you to have a good visualization of this. Okay. So now we are going to calibrate it. Okay, now we're going to come down. And now, as is our custom, we are going to put north in the north direction. Normally I have this done before you guys tune in. Okay, but this time I couldn't do it because, right, we had to do so much development that we're just now getting the thing working. Okay, so watch this. We are going to roll. Boom! Do you see how beautifully this is rolling? And remember earlier how it was kind of had a little glitch? With the Quaternions, that glitch is completely gone. Also, remember that if we rolled all the way 90 degrees, it would all of a sudden flip around and go crazy. But you see, I am rolled 90 degrees, and with a 90-degree roll, I can still change the orientation. We can go upside down, we can face the other way, and we can twist it. We can come back, we can go nosedive, okay? Yeah, I killed it with the nosedive. You know what's happening? I've got a little bit of a not good cable, and the way you fix this is if you have this problem, you do try and accepts in Python, which we really haven't talked about yet, but it is, if it reads a bad data point, then it dies, and so we'll start it here again. And we're probably going to have to go and get our orientation again, which I apologize for. Okay, we'll zoom out. I'll get it over here like this. Okay, now let's make north north. Okay, get our camera kind of lined up a little bit better. I'm just trying to get the visualization to kind of match. All right. So roll is roll, roll is roll. Now we were in the process of doing the nosedive. Okay. And the nosedive is kind of killing it. Probably I need to try and accept, because I'm probably doing an arc tangent with 0 in the denominator is probably what's happening. And so I need to just kind of clean that up a little bit, but I won't go a complete 90-degree nosedive this time. But you guys can play around with it. Let's get it oriented again. Oh man. I am going to reset this thing. I hate doing this, but you know what I'm going to do? I'm going to do a try here. Can you see my code? Let me show you. If you start getting little glitches like that, for some reason it's getting some bad data, and when it gets bad data it crashes. So I'm going to do a try like that. So this is saying do a try with a colon, and now all the rest of this I'm going to need to indent. So I will come over and I will say view, and I will say edit source code. Edit source code, and I will say indent block. So that will get my, that unindented. Edit source code, indent, and now I need to indent again. Source code, indent. So what does this mean? It's just the try has to be indented from the while, and now all this other stuff needs to be indented. And try, and then what I need is an accept, and then I just say okay. If it crashes, then just pass and try again. So let's see if this will work. So I'm not sure why all of a sudden it's getting a little bit of glitchy data, but this should take care of it. Okay, let's get the view where you can see it. Okay, and I think we want to come back over here now. All right, so we'll back off a little bit. We will scoot it down, and we will scoot it over. Okay, now let's get this crazy thing calibrated like we do. Okay, let's point north to north, and then I can bring it down, and I can kind of zoom in a little bit. Okay, now get my camera lined up with it. All right, so rolling is rolling, pitching is pitching. Now let's do the nosedive. Okay, and we did the nosedive. Did you see that? Okay. Now, as I'm nosedived, you see that I can rotate it in the nosedive position. Probably if it's exactly at 90, it's probably glitching out a little bit, but you see if I just tip it a little bit further. Okay. Also, look at this, man, in the complete roll position and rotating. Nose all the way up and back upside down. Boom. Okay, guys, do you see with these Quaternions and this BNO 55 how smooth the data is? Look at how just silky smooth that is. And really, it's just amazing to me to be able to go to these orthogonal axes without having the thing crash. And so this has been fun, guys. I'm sorry this has been a little bit of a tedious lesson, and I'm sorry we had a couple of glitches in there that I kind of had to on the fly figure out what was going on. But you guys were patient. I appreciate that. You guys, let me know out of all of you, how many people made it through all 21 lessons, because this is we're kind of to the end point here. Although now that we can really understand, it's just like I can't quit. I can never quit. Maybe it would be interesting if we tried a few lessons after I recover from this Quaternion one, where we take this data and do something with it. Like maybe we could point a camera, or we could mount this thing on our finger, and then as we move our finger, have something affected in the real world, because we have solved it now, man. You have been to the brink. You have dipped your toe in the imaginary room, and you found a real number line in there. You have been to Quaternions and back, and you're still alive. That's pretty darn good. I'll tell you, I have actually been working on this problem for about 6 years, and it's only now that I've really gotten it where it really works, where I figured out a way that you can really do this in any orientation and have it really work. And so I had a lot of fun with this. Guys, leave me a comment down below. How many of you, this was like a crazy hard series of lessons to do. And sometimes I'm worried about doing something that's this crazy hard. I feel like people are just going to drop out in the middle, and then I'm just going to kind of be wasting my time doing it because no one's actually going to finish it. Tell me, do you like harder projects like this? Are you guys willing to dig in and do harder things like this? I really showed you everything you needed to do it. I figured it all out for you. But is it too much to follow lessons like this? Would you rather go back and blink LEDs or play around with the Raspberry Pi or make the buzzer go off, or would you rather do things like this? Okay, guys. Paul McQuarter from TopTechBoy.com. I will talk to you guys later.